Hi Year 12s. In this video we'll be talking about subtopic 3.7, esters. So things are getting a little bit more complicated. Our structures are going to be a tiny bit harder to name, but we'll give it a go. Now, esters are formed when carboxylic acids have a condensation reaction with alcohols. Now, what we'll need to be able to do is we'll need to be able to, first of all, identify esters, and then we'll have to name them, but only like a small subset of esters. So it says here we have methyl and ethyl esters, so that will hopefully make sense very soon. We'll have up to 8 carbons in the main chain, and then we'll have side chains that are limited to 2 carbons. So that bit there is similar, and hopefully the rest, this first ethyl and methyl and ethyl ester bit should make sense too soon. What we'll need to do is we'll also need to be able to draw an ester given the alcohol and the carboxylic acid that they came from. Also back the other way. So if you're given an ester, you should be able to split them apart. You should be able to split them apart and draw the alcohol and the carboxylic acid that would have come from. And last bit is if we have a last bit for this first section is that if we have a polyester, so that's a type of polymer, you should be able to identify the monomers, the first things that make them up. So it'll be we'll talk about it a bit more later, but we'll be able to break them up into separate monomers. Now, getting started. As I said before, we have our esters. So they form from the condensation reaction between an alcohol and a carboxylic acid. Now, the condensation reaction means that we're going to be losing a molecule of water. And that molecule of water comes from one hydrogen from the alcohol and the OH from the carboxylic acid. So that means what we do is we end up joining this oxygen here to this carbon just here. And the alcohol will contribute the alkyl group, the bit on the end sticking off the oxygen. And the carboxylic acid will contribute this carboxylate component, so this right-hand side here. Now, you'll have to remember that the alkyl group, the bit that we name first, which again we'll practice in a minute, but the bit that you name first is attached to the oxygen. The way I remember it is the remainder of the molecule is a carboxylate, and we have already learned about carboxylates in chapter subtopic 3.5, which is just this piece here where we have a carbon chain with a C double bond O and then an O, so our carboxylic acid, but we don't have the oxygen, the hydrogen attached to that oxygen at the end. Now, when it comes to naming them, you'll have to again identify that alkyl bit and the remaining bit. So we have just a generic naming scheme just here. So we have alkyl carboxylate. So you identify the alkyl group, and you throw that name down, and then once you've identified the carboxylate, you'll put the name of that down as well. So we'll have a bit of a practice. So we'll start with this first molecule. We see our ethyl group is our alkyl group, so the bit hanging off the oxygen. So 2 carbons means ethyl, so we will put that in here. So ethyl will be our first bit. Now, this bit here has 1, 2, and 3 carbons. So that is a propanoate group. Again, it would be propanoic acid if it had the hydrogen on here, but removing that hydrogen gives us that propanoate. And so that is the second half of the name. So this molecule is ethyl propanoate. Now I wanted to do, because we are able to have side chains, so I wanted to do an example with side chains as well. Now I'll use the same scheme where I highlight the bits. So we will only get up to an ethyl group. So you could have one carbon and an ethyl. Sorry, actually, you know what I might do? I might show you that just here. So if it was like this, that would be a methyl group. But because it has that second carbon, this becomes an ethyl group. So while I'm here, I might as well just chuck in, so that bit there becomes an ethyl group. Now the second part is going to be a little bit more complicated in this case. Oops, sorry, there we are. This whole chunk here with our carboxylate, it does have a bit of complexity because it's substituted, but the same naming scheme applies for our carboxylic acid. So we need to identify the longest chain, and so that could go start from up here, but I'm going to it could go up to the top, but I'm going to just go in the zigzag in the page just to make it more simple. So we have 1, 2, 3, 4, and 5. Now, again, the reason why we count from that left-hand side is because that the carbon directly attached to the double bonded to the oxygen and directly attached to the other oxygen is going to be carbon number 1, and everything goes from there. So we know this molecule is going to be a pentanoate. So actually, might as well chuck that in here, pentanoate. And hopefully we have enough room to write the rest of it, but we'll see. Now, we have an ethyl group. So this ethyl group is the one that's at the top here. So I'll just use this one here. So this ethyl group here and this methyl group. Now, again, the same naming scheme applies that we've dealt with before, and that is we are going to write down the name of the substituted parts in alphabetical order. So ethyl will be first. So in this case, it'll be an ethyl group and it's on carbon 3, so it'll be a 3-ethyl. And then the other group is coming off of carbon 2. The methyl group is coming off of carbon 2. So it'll be 3-ethyl, 2-methyl. You know what? Let's just do some erasing. I know it's going to be a bit of a mess, but we'll deal with it. I'll fill it in. Actually, I'll have to fill it in beforehand because otherwise it'll look a bit weird. So, whoops, while we're here, let's make this a bit extra long so we don't have to worry about it. And hopefully I actually made it longer, but we'll see in a second, won't we? So it was 3-ethyl, 2-methyl, pentanoate. And I squeezed it in there. Didn't give myself much room there, but either way. So ethyl, 3-ethyl, 2-methyl pentanoate tells us that we have an ethyl group on one end. We have an ethyl group on one end, and then we have 3-ethyl, 2-methyl pentanoate. Tells me I've got pentanoate, so 5 carbons, and then on carbon 3 is an ethyl group, and carbon 2 is a methyl group. So that's pretty much as sort of complicated as it's going to get. You can go up to 8 carbons long, and then you can have multiple groups, but the naming scheme is what we've practiced before. Now, now that we've named them, we're going to go down to this next step, which will be picking 2, so just a random alcohol and carboxylic acid, and we're going to join them up. So we've got ethanol. Ethanol contributes an ethyl group to the end. Our propanoic acid contributes a propanoate. So you need to be able to draw those two combining together, losing the hydrogen off the alcohol and the OH off of the propanoic acid to give us ethyl propanoate. So again, it might actually be, exactly what we made, exactly what we named earlier. Cool. Now, when it comes to dealing with the extended polymers, so like polyesters, they are going to be created when you react specific molecules. So a diol, so a molecule with 2 OH groups at some point on them, you will react those with dicarboxylic acid. So both of those we've seen in their respective sections, in the alcohol section for the diols and the dicarboxylic acids in the carboxylic acid section. So here we have our diol. So this would be just for the fun of it. So we have 3 carbons in this chain. So meth, eth, prop. So this will be propane, because we have a diol, so they end up with an E. So propane 1, 3 diol. Now, on carbons 1 and 3, so the ends, you have OHs. So we go name 1, 2, and 3. So propane 1,3-diol is the name of it. Now, this next one, so we have 1, 2, 3, 1, 2, 3, 4 carbons. So meth, eth, pro, bute. So this will be butane. Sorry. Sorry. Butane dioic acid. Now, we don't have any numbers in this because the carboxylic acids are terminal, so they are on the ends. So butane dioic acid is going to give us that structure there. Okay. Good. Now, when you join these two together, what you'll end up with is the sorry, I'll get the laser pointer up. You'll end up with these bits here getting removed as water molecules, and you'll end up making a join, an ester, like an ester joint. Now, if we do that, you see this new join that's been made, and on the other end, so when this reaction happens, you'll have these two ends joining, and on this end, you'll have another alcohol coming in and making a joint on that side. So you'll see a join here and a join there. On both sides, you have the alcohol base, and in the middle, you have our carboxylic acid base. Now, this will continue on until something stops it. Either it joins to itself, or some contaminant comes along and joins to stop the chain reaction. But either way, whenever you join these, you're going to notice that you'll have a 1, 2, 3 carbon section because we are dealing with a propane diol, and then a 1, 2, 3, 4 carbon section because we're dealing with a butane dioic acid. Depending on which one which diols and which dioic acids you are dealing with, that will change the structure of this molecule. Now, we're going to have a chance at... Oh, actually, I did already. There you go. I thought I got ahead of myself. So the names of these molecules I did up there, but I forgot that I actually wanted you to... I wanted to do it for you down here. But they are the same molecules that I had up there. So I'm just going to fill in... those. And you know what? Might as well just erase those. You can see them in the video, but they don't need to be there in the notes. If I'm lucky, I might be able to... Oh, there we go. I knew that would happen. I'll deal with that later. No big deal. Actually, I think I can do it. Here we go. There we go. Be a bit more precise. There we go. And let's continue. Now, I've shown the overall part just up here, but I thought I'd break it down a little bit more down here. So we have our first reaction will be joining these two together, which will make this molecule here. If we add it to an alcohol group on this other end, we are going to join it into this original section that we made, plus continuing on, and that step will happen over and over again. So it's what I mentioned up here before, but what you'll normally see is an extended version, so they won't actually break it up into multiple steps. Okay, so now we have our second part. So when we actually go to make these esters, you need to know that they don't happen, or this reaction doesn't happen very quickly at 25 degrees Celsius. So if we're at room temperature, you put those molecules together, nothing's really going to be happening. So what we need to do is we need to heat them up. So we need them to be a bit hotter. And when they're hotter, the reaction rate goes up. So what we're going to do is we're going to use a particular method, and it's called reflux. Now this method called reflux will be combined with some concentrated sulfuric acid, a small amount of sulfuric acid, which is a strong acid. We're going to combine those together to allow, first of all, catalyze it with the sulfuric acid, heat it up to increase the reaction rate to hopefully make our esters form. Now, as I mentioned reflux before, now reflux is a particular process where we take our reaction mixture, we put it into a round bottom flask or something similar, and we heat it. Now, the problem is that to get it as hot as possible for whatever solvent it's in, it's going to boil. So it's going to boil. That will allow us to get it up as hot as possible. The problem is that if we didn't do anything differently, and we just had that container and we just boiled it, all of our reaction contents will just disappear into the air, which will mean we'll have nothing left. So what we do is we put what's called a condenser tube on top. Now that condenser tube is as the name suggests, it's a tube that goes up. So you can put something in, or or stuff can come out. But the walls, it's actually double walled. So we have a wall in the center. We actually have a wall around the outside, which you can run water through. So as you can see here, we've got a tube going in and then a tube going out. You run the cold water in the bottom. That will make this bottom part nice and cold. So when the reaction mixture comes up here, it'll touch the walls of the glass, which are cold, and will, as expected, when it touches the cold walls, it will condense, turn back into a liquid, and then drip back down. So you'll end up with like a constant dripping back down into our reaction mixture. What this does is allows this bit here to be nice and hot without the risk of losing all of our contents. Now, as the water goes through, it's going to get heated up by the reaction mixture, and it's going to come out warmer. Now, not necessarily hot, but its temperature will be higher as it's absorbed the heat from the evaporating or boiling mixture. Now, as I mentioned again before, the sulfuric acid that we add is just a catalyst, so it's a strong acid, which means you put it in and you get lots of hydrogen ions, but the concentration doesn't have to be particularly high. So this bit here is the process of making the ester. You also need to know information about breaking it apart. Now, we're not necessarily the reaction conditions, but you need to know that they can be broken apart. So if we take our ester, water is a molecule that comes out when we form the ester, so it makes sense that hydrolysis, the process of adding water back in, is going to be the process how we break it apart, and that is the case. So if we had our water, we can add the water in across this bond and remake our carboxylic acid and our alcohol. Now we can do this process under like two conditions. First of all, we can do it under acidic conditions where there's lots of H+. And if we do that, we're going to liberate a carboxylic acid and an alcohol. Now, if we change the conditions, so we put it under a basic condition instead, now the difference will be that we liberate a carboxylate ion. So in a basic condition, this carboxylic acid, as the name suggests, acts like an acid. It loses its H+ on the end, leaving us with an O-. Now, we have, again, the last summary of this process. The hydrolysis that we do, the products will depend on the reaction conditions somewhat. So if it's catalyzed by an acid or a base, you're going to end up forming slightly different products, either a carboxylic acid and alcohol, or a carboxylate ion and our alcohol. Now I think that's pretty much it for this topic, so I hope it helped.